Hi friends, let us see another problem. The stress strain curve of a material is given as in this diagram. Up to here, it follows Hooke's law, means a linear elastic curve where the stress is directly proportional to the strain, and from here it starts yielding and reaches to a maximum upper limit of A point A where the stress is 500 megapascals. Because it starts yielding, if we release the stress, it doesn't come to its original position but races to another path. So here when the stress is released, it comes to a point B where the stress is 100 megapascals. The strain at A is given as 0.5. We need to calculate the strain at point B, and Young's modulus is given as 200 gigapascals. Okay, in order to calculate the strain at B, we know that the entire the value of strain at A. So if we subtract the value, the strain value corresponding to this length in this diagram, we will get the strain at B. So this is 0.5. We need to calculate this value. So if we see, this forms a triangle, and the Young's modulus E holds good to the relations stress by strain is Young's modulus only for Hooke's law valid curves, means the curve which is straight. So here the AB curve follows that linear pattern, and the slope of this line AB, because slope is opposite side by adjacent side. Opposite side is stress, adjacent side is strain. So stress by strain gives Young's modulus. This is the slope of the line AB. So tan theta, this is the slope, right? Tan theta is opposite side by adjacent side. So Young's modulus is stress at B is 100, stress at A is 500. So stress corresponding to this, means this height is given by 500 minus 100, so 400. So stress is 400. Strain value, this is strain, this side that we don't know, and Young's modulus is 200 gigapascals. Because stress is in megapascals, so if we convert that, gigapascals is 10 power 9 pascals, right? Megapascals means 10 power 6, so into 10 cube megapascals. 200 to 0. If strain goes there, strain is 2 by 10 cube, means 0.002. This is the strain corresponding to this length. Now strain at B is 0.5 minus 0.002, which is 0.498. Okay, now let us see the set 2 questions. A bimetallic cylinder made up of steel and aluminum joined together is clamped at both ends of same length of L by 2, and this is subjected to a force P at the junction. Okay, the area of cross section is given 1 meter square, and Young's modulus of both materials are given. The strain in steel and strain in aluminum is given. Obviously both strains are equal because both are clamped. How much it will get elongated, this will support that much deflection. So both strains are same, and it is given also. Now we need to calculate the load P, not stress, the load P for this corresponding strains. Okay, because both strains are same, we know that strain for each bar is let us first draw free body diagrams of both these individually. See, the load P is not responsible, the same P is not causing the stress in steel and aluminum, because both Young's modulus are different, both are made up of different materials. The stress corresponding, the stress means the resistance to the applying force. So the resistance caused by steel and aluminum to this particular P are different. So for steel it is tensile, let us say PS, and for aluminum it is compressive in nature, right? So it is PA. Sum of PS and PA, these two will give the P. Okay, P is distributed as PS and PA for both these materials. Okay, PS plus PA is P. So PS is P minus PA. We know that strains in both these bars are equal. So strain in steel equal to strain in aluminium. So PS by AES equal to PA aluminium by area of cross section into area of cross sections are same. So PS by Young's modulus of steel is 2 gigapascals, and aluminium is PA is nothing but P minus PS. So EA is 70 gigapascals. 3. So PS equal to 3P minus 3PS. So PS equal to 3P by 4. Okay. Okay. Now the strain value in the steel bar is given as 10 power minus 6. Strain equal to P, same one. PS is 3P by 4 into A is given as 1 meter square into Young's modulus is 210 gigapascals. If we turn it into pascals, 10 power 9, because we will first see everything in newtons. Okay, 370. So P is 280 into 10 power 9 into 10 power minus 6. Minus 6, 3 gets cancelled, 10 cube is remaining. So 10 cube corresponds to kilo. So 280 kilonewtons. Okay, we are asked to find in kilonewtons. Okay, next problem. True stress versus true strain relationship is given as in this equation, and the initial cross section of the bar is given. We need to calculate the final area of cross section. See, the simple relation stress equals to Young's modulus into strain is an engineering equation. It doesn't validate the true variations of the cross sections and dimensions of the specimen. So true stress and true strain formulas are somewhat different from the conventional ones. Okay, here the true stress is given in this equation. We know that the standard formula is K into e power 0, here 0.4, and true stress is given by multiplication of constant and e power n, where n is a constant, n value is the strain itself. N value is the tensile strain only at ultimate tensile strength, because from there the deviation doesn't happen because material fails itself. So the power, the n is the at that point only for the ultimate tensile means at that point of ultimate tensile stress. Okay, here the material is subjected to failure condition. It is given in the problem. So in this question the n is 0.4. The strain is n and it is 0.4. We know that we know that the true strain formula is log of ln of final dimensions by initial dimensions, length, or ln of reverse, area initial by area final. Okay, now area initial is given 100 by AF and the strain value is 0.4. So here the base is E, so e power 0.4 is 100, then 100 by AF. So e power 0.4 is 100 by AF. So AF is equal to 100 into e power 0.4, which is around 67.032 mm square. Okay, this is the final value.